Swayam Prabha. Digital India. Educated India.
Welcome to this summary lecture for the course on bioreactors, the NPTEL online certification course. This summary lecture would provide an overview of the things that we looked at in this course, and hopefully it will improve the understanding and appreciation of the material here. We first began with an introductory module. There were totally 5 modules. The first was introductory module. The second one looked at 2 major outcomes from a bioreactor: the cells themselves, or what are known as biomass, or the products made by the cells or through enzymatic reactions. The third module looked at analysis of a few common operating modes of the bioreactor and inherent advantages in operating them in those various modes over the other modes. The fourth module looked at the bioreactor environment parameters, the variables that are usually measured and controlled to make the bioreactor operate optimally without understanding the actual factories that are inside the bioreactor to a great extent. Some surface level understanding is there, but to a great extent it's not understood, and the bioreactor environment parameter operation level is limited to that. Then in the last module, module 5, we looked at some means by which we can understand the cells themselves, what is going on inside the cells, hopefully to manipulate them towards better production of substances of interest to us. That is the overall scheme for this course. Let us summarize some details from these various modules. The introductory module, we first saw what cancer was and the drugs that are used to treat cancer, the monoclonal antibodies, and we saw that MABs are made through bioreactors, through a bioprocess of which bioreactor is the important part. Similarly, this is another example: alternative liquid fuels such as bioethanol and biodiesel. Also, bioreactors play a major role in them. Insulin, which is a drug to treat diabetes, is made through bioreactors, and even yogurt is made through bioreactors, simple bioreactor at home. Then we looked at the bioprocess, the bioreactor, the common bioreactor types that are used, such as the stirred tank bioreactor, the airlift bioreactor, the packed bed bioreactor, solid state bioreactors where there is no liquid usually, single use bioreactors such as disposable plastic vessels, and wave bioreactors, which are good for certain operational reasons in the industry, and photobioreactor, which is used for cultivating photosynthetic organisms. These all we saw, and we said that there are many other kinds of bioreactors also. These are some of the common ones. Then we said that the bioreactor could be operated in a few operation modes: the batch, where we dump everything in, let the process happen, and dump everything out and proceed with processing. Continuous operation, where there is a continuous input and a continuous output. We are usually interested in the steady state operation, which occurs for most of the time. The initial paths could be at unsteady state, and the startup and the shutdown paths could be at unsteady state, which we are not normally interested in. And then the fed batch operation, which is somewhere in between a batch and a continuous operation, maybe intermittent input or intermittent output, or both. Then we looked at the need for a clean slate. First we kill all the microorganisms in the bioreactor, then introduce the microorganisms of interest so that they can grow well and produce the product of interest to us. Some of the means of achieving a clean slate is high temperature, chemicals, and radiation. We looked at some kinetics corresponding to the high temperature sterilization or thermal sterilization, the concept of decimal reduction time, the basis of that, I will not get into that details in the summary. We looked at the material balance basics and so on. Yes, this was the time that it takes for the cell concentration, the time taken for the cell concentration to go from a viable cell concentration initially xv naught to a final viable cell concentration xv 2.303 by kd. This is a constant log to the base 10 of xv naught by xv. And then we saw the concept of a decimal reduction time, which is the time taken for a tenfold reduction in the viable cell concentration at a given temperature. These can be used for design purposes, and that is where we finished up module 1 with a practice problem and a solution to that. Okay. Then the module 2 looked at the two major outcomes from a bioreactor or a bioprocess, which are cells and the bioproducts. And we saw examples where cells themselves could be important bioproducts, and otherwise there are many other molecules that come out of the cell. The models for growth when cells themselves are the bioproducts, or each cell is going to produce a product, so it makes sense to have more of cells, more concentration of cells, and therefore in any case growth is important for us, or in either case growth is important for us. This is the simplest model, Rx equals mu x, a first order representation. Mu may or may not be a constant. It is a constant in certain situations, it's not a constant in other situations. And then we looked at one other model, the logistic equation, and then we said there are more complex models that are available for people who are interested in advanced level learning of this aspect. Then we said substrates are converted to products, and then we looked at some important concepts such as a limiting substrate, and its relationship to specific growth rate, or the dependence of specific growth rate on the substrate concentration, which is given by the monod model. And then we said there are other models available also, such as the Moser model, the Andrews and Nowak model, or the model that gives the limitation of two substrates simultaneously, or Jerusalemsky and Neranova, which looks at the product inhibition. Then we looked at a model for product formation kinetics in the bioreactor, the Ludeking-Pire model. Then we looked at what yield coefficients were and how they can be used to interconvert one rate to another rate, interconvert rates. Then we looked at the concept of maintenance. The substrate, we said, needs to go towards cell multiplication as well as towards cell maintenance of metabolism, transport, genetic processes, and so on. So that is taken into account, especially when the substrate concentrations are low, and some ways of taking them into account have been given here. Then we looked at enzymes. We looked at enzyme kinetics, the Michaelis-Menten enzyme kinetics. You can go through it in detail. I'll probably show you the final derivation or the final equation, which is this V equals P max S by Ks plus S, the same form as the monod equation form, but of course this is entirely different. And also that V max is K3 times E total, and Km, the Michaelis-Menten constant, is K2 plus K3 by K1. These correspond to the rate constants of individual steps in the mechanism. Enzyme plus substrate giving you enzyme substrate complex, which further gives you enzyme and enzyme back and the product of interest. So this is the representation in a graph, and then we found out a way to find out the model parameters Vm and Km by the Lineweaver-Burk plot and the basis for that. and we also did some practice problems 2.1. Then we looked at different kinetics, other kinetics, especially the competition kinetics. We said that there could be three kinds of common inhibitions: competitive inhibition, non-competitive inhibition, and uncompetitive inhibition. In the competitive inhibition, the inhibitor binds to the enzyme and thereby inhibits the rate of the reaction. In the non-competitive inhibition, the inhibitor binds to the enzyme as well as the enzyme substrate complex and inhibits the reaction. In the uncompetitive inhibition, it binds only to the enzyme substrate complex and inhibits. And in these three cases, the Vms and Kms change. Only Vm changes for competitive, only Km changes for non-competitive, and Vm and Km change for uncompetitive. Then we looked at enzyme immobilization, whereby we can minimize the damage to the enzyme, but it comes at a cost. We also said that cells could be immobilized. These have been used industrially in an immobilized mode. Okay. That is what we essentially saw in module 2, and we also worked out a couple of problems. Hopefully the problem solutions would have been useful. The methodologies would have been useful. And then in module 3, we looked at the analysis of common bioreactor operating modes, the batch mode, the continuous mode, and the fed batch mode. These two we looked at in great detail. Fed batch, I just introduced you because it is complex. I just introduced you a way of approaching that. So in the batch mode, we did balances and we got expressions for the time of a batch, for the time to reach a certain desired cell concentration, starting from a certain initial concentration, and that was 1 by mu ln of x by x naught. X is the desired concentration, x naught is the initial cell concentration, T naught is the lag time, the sum of these is the batch time. We worked out a problem to illustrate that. And then we brought in the effect of substrate concentration on the specific growth rate and saw how things could change when that has been brought in. It could be relevant in some situations, but it is more important for the continuous bioreactor situation. So when we went and analyzed the continuous bioreactor, we got some very insightful good insights into the operation, and we said at steady state we obtained conditions for steady state operation. We obtained the critical dilution rate, which is the maximum operable dilution rate before washout occurs, and we also obtained an expression for cell productivity in a chemostat and compared it with the batch bioreactor productivity. We said that this specific growth rate equals a dilution rate at steady state operation. Therefore, an operational parameter such as flow rate and dilution rate is flow rate by the volume. So the flow rate can be used to control the biological parameter, which is the growth rate. That's the significance here. And then we obtained a critical dilution rate beyond which there is actually no cell production by the cell. And then we said that a chemostat is inherently 3 to 4 times more productive than a batch bioreactor. Although it's a lot more difficult to operate a chemostat, it's a lot more intensive to operate a chemostat. Then we looked at means of analysis. We of course worked out some problems. Then we looked at a brief method of analysis, or analysis in brief, of a fed batch operation where there is only input. Very briefly, if we know the functions of the variation of the flow rate, input flow rate with time, and the variation of the input cell concentration with time, then we can use this equation to design appropriate aspects, is what we said. Okay, so that was module 3. In module 4, we looked at cultivation parameters that affect bioreactor performance. The cultivation parameters were temperature, pH, medium composition, aeration and agitation, and dissolved oxygen level. Dissolved oxygen level we looked at in great detail, including a KLa measurement methodology, the dynamic response method. We also worked out a problem by which we got a better appreciation of the KLa determination. Then we looked at some aspects of scale up and scale down. We said that we need to maintain the equivalence of geometric parameters and the equivalence of operational parameters during scale up. Only then can we expect at least that whatever results we got at a lower scale would be applicable at a higher scale. And the scale down is important because it gives us a means by which potential strategies to improve the existing process, such as changes in medium composition, new or modified production strains used, or operating conditions, different operating conditions can be tested. And the validation of new operating procedures for cell culture products can be tested without taking time off the production bioreactor and without too much cost. So that is the advantage of scale up, scale down. I've given you a lot of references which include videos, websites and papers to provide a lot of background which would be interesting to people who want to know more about those aspects. Then finally, we looked at the cell view of the bioreactor, because cells are the actual factories that are producing the product. We said that we would look at the cell as a black box initially, get some insights using bioreaction stoichiometry, then open a window through cellular indicators such as redox state, energy state, and probably intracellular pH. And we can use those as control variables also. That's what we saw. And then we looked inside. We spent a lot of time looking inside through one technique called metabolic flux analysis, and we saw how it provided us directions to appropriately genetically modify the organism and actually achieve threefold increase in yields. This was a paper by Valeno and Stephanopoulos. And then I very briefly mentioned how the rDNA technology can be used to change what is inside itself, or probably we can look at techniques by which the entire cell is changed, such as the hybridoma technology. Right. So hopefully you had a course that would be helpful to you. Hopefully you had fun during the course and you enjoyed the course. If you need anything more, do write to me. Wish you the very best and all success.